Welcome back to Raw, Unedited channel. So it's late at night. Well, no, not really. It's more like 12:02 a.m. So the wee hours of the morning have just begun. Um, I have more stuff from AliExpress and some others. So first of all, this computer is going to change again. It's having USB problems. It's just too old. It's too bad because it is very rock stable. It works perfectly, but I can't connect stuff to it. I run out of bandwidth. My USB capture doesn't want to work. I mean, yada, yada, yada. It's like on and on and on. So, what I'm going to do, and where did I put it? Here we go. So, this is going to be built. So, we can have a look at this. So, here we go. 1 gigabyte. Now, I have the 570 X570 Aurorus Elite over there, but I still think it has some of the features that even this one now has. This is like really neat. I had a look at the motherboard manual. Now, if you're going to build a system, RTFM. So let's have a look. Doink, doink, doink. So I was kind of impressed. Our board here is 4 memory slots, and I picked it because it has lots of different USB hubs. So according to this here on the USB, so we've got CPU has USB, so 4 times USB 3.2 Gen 1 ports on the back panel. Chipset has a 1 times USB Type C, a 1 times USB 3.2 Gen 2 Type A, 2 times USB 3.2 Gen 1 ports available through the internal USB header. So I have that piece on the front of my case. Then again, chipset plus one, we have a USB 2.0 hub, and you can actually see it on the diagram. They mark it right here in the corner. So that's like 3 different hubs, maybe even 4 different hubs, depending how they handle this, which is what I was after. Because I've still noticed, still in Video for Linux, no matter what they do, you put more than one webcam on a hub, you run into issues. So I'm hoping this will solve it. Now, I haven't even cracked the bag or anything, and I won't do it because I don't have all the parts here yet. But I will change out possibly 2 or all the SSDs in here for the one NVMe I picked up. So I picked up is it a Crucial? Or Sabrent, I think it was. It was a good price. This was a really, really good price. Um, this board was on Amazon for $146.99. It supports all the current Ryzen CPUs, and then on top of that, I picked up a what was it called? Oh yeah, 3600. I should be able to see it from here. Let's go and say I'm going to turn on the properties of Chrome. No, not console. Come on, guys. This one. So, orders, returns. And let's see. Secret login. I promise I won't show you. You'll be, what did you buy all that stuff for? Okay, here we go. All right. So I picked up, yeah, the Sabrent Rocket 1 TB, 3200, 2000, which is pretty good for this price category. Like, I mean, if you want, you can see $157 for this, for that kind of speed. Some of these ones, once you jump up to the 4,000, 5,000 type, or even the 7,000, the price just goes through the ceiling, of course. Right? Now, this guy here, 304. So my board and CPU, 404, 450. So a CPU and a board. And yes, I could have gotten some faster or whatever, right? But I picked this one because it has a 65 watt TDW, whereas the 3600X, which I could have bought for not much more, has a 95 TDW. And the object of the game for this machine is not 100% speed, it's more quiet, dead silent. Don't want to hear it. I'm not one for lots of noise. Now, another item I had picked up, which was really handy. If you go through cans of air all the time, blowing things out, keyboards, whatever, um, this guy right here is worth its dime. It is, well, on J2 Sense, he has a wall powered version, a bigger one, but this is a lithium battery packed. And the one I have at work, I've yet to recharge the thing. Every time I pick it up off the shelf and go use it, it works perfectly. It's like, wow, very, 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 very power efficient. And it's $100, but considering that a little can of air like this thing here, there, right there, see, dust off. This little measly can, which you can go through pretty damn quick, it can be, depending where you go, it can be $8 to $12 a can. Yes. So at work, we were buying boxes of 12 cans at a time. I think I got them at Computer Plug, and there might be I think about $45 a box or something like that, $50 a box. A couple of those boxes would get wiped out in no time flat because people come around and take the can, blow the keyboards out, and use lots of air doing it, right? And I got this instead because it's cheaper in the long run. Um, what else? So I did pick up some more storage bins of this size. Um, they're really nice. These guys are. I would highly recommend these guys' bins. They're well made, well packed. They came. None of them ever cracked. I This is the 6 liter one. I also have the 3 liter version of the bin. Um, and they work great for storage. And for some stupid reason around here, um, I am short of old style. I've got tons of this cable here, this one, right? And I've got tons of the USB-C, and I've got tons of the was it mini? Micro. But the minis, I was a little bit hard pressed to find some minis around here the other day. A couple of them I had kind of were broken, the cables, and they were stiff, and I really, really like these braided cables. These guys right here. They're flexible, they drape easily on the desktop, whereas the old style, these guys are the PVC, they're stiff. This one's not too bad, but it's also the ideal length for the bench. See? Not that long. Like we're talking 1.5 feet or whatever in metric. Um, they were handy. So where did I put the motherboard in? We can't lose the motherboard manual. Never lose that. And this box is heavy, by the way. Weighs something. So I picked up some more these cables in a ribbon form. Also, I've been meaning to want to get myself some little pads. I've been using these guys white blah like this. It's from some trade show I went to like more than a couple of decades ago. Yeah, and I wanted one with grid on it, so I picked up some gritty paper here in this form of sticky notes. So yeah, let's turn that off. We don't need Chrome anymore. So AliExpress stuff. First one I finally got. My stock of chips. These are all the ones I bought. They were only, a couple of bucks per 20 or something like that. So this is what they look like. So that's 74 HC 10 ends. Ends just it means a dip package. And then we got these, and these, and these, and these. All these. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 basic TTLs across the board. ANDs, ORs, NORs, ZORs, shift registers, both directions. So what they call SIPO, serial in, parallel out, and piezo, parallel in, serial out. So for both directions. Now, I have these sheets of foam up there. I have one sheet left, I think. I'm going to populate it with chips. It's conductive type of foam, right? So I find that you don't want to damage these things from any static way. You just store them in that. So next item that we have here. So this. Yeah, we don't need that. So this is a touch screen that goes on a Raspberry Pi Zero. I wonder if I can just turn this a little bit. Yeah, like that. So now the only thing, I was reading the instructions on one of these, and I don't know if it was this one or not. So one of these had this notion that I should put custom version of an OS on, right? So there we go, right? And there's a little stylus. I have one of these for Arduino, for you can stick on top of a Uno to do exactly the same thing. And I've had it working before, so I'm gonna try this one out, see how it works. It was not really expensive. I think $10 or something like that, $12. Then we have this baby. So there's several items in here. We begin with these things. And these things. And if you recognize them, they're connectors. And just get these into their bin here. So they're similar to the black connectors, but they're smaller. Now, I don't think they're the smallest. I think they're more on par with these guys right here. So that's a 2. And I need a 3. So let's find a 3 here. Right here is a 3. Helps so don't plug it in the wrong way. Yeah, we'll go like this. So see? Like so. So there's the pins for it. There's the connector for it. And of course, as you can see in this thing, pins have dropped all over the place in here. Well, no, actually not too bad. Not in this one. So, and then this one here, during transit, of course, you can see right here, blink. Now, this would be interesting, putting one of these wire on one of these. But I have the wire for it, so those are those. Then we have this one. DuPont connector kit, of course. Let's put the Funhouse back over here again. And then in here, of course, I got it as a kit. The crimper. Just what I need, right? Another tool. So here we go. Let's go and there we go. There we go. Oh, Oh, there's some ribbon in there. I'll collect this up later off the floor. Uh, ooh, ooh, that is a tough connector. So, get a bunch of ends, bunch of ribbon. It looks like our dividers here shifted out. Huh. So, let those go in there. Those go in there. So, take all those out. I might just shift all these into the bin where I have all the style of strip connectors like this. That is a 2. No, that's a 3. That's a 4. I think this is what happened. 2s and 3s got mixed up over here. So, yeah. So what's supposed to happen down here, of course, getting these little walls back in place is like really hard when all the stuff is in there. So let's see if we can do this. Nope, it didn't work. That's a big one. That's like this size. That's that size. Let's do this. Move it all the way over. That doesn't belong in here. That goes in there. That goes in here. That goes in here like so. That doesn't belong in here. It goes in here. That doesn't belong in here. It goes in here. Yeah, this bin poured over into this bin, basically. Right? So this will go there. And all these guys. These are all 3s. So you got, I think, singles, doubles, triples. And come on, boys, in you go. Yes. Feel like I'm calling a dog. Here, Ralph. Okay, here we go. And then what we do in this compartment here, this is another 3. We will put these 2 guys here. And there we go. And that was a 3. Okay, so and a 3. And over here, we'll just shuffle all these over because there's another door plate. I figured as much. And we will see if we can get it down there. Yes? No? Yep. Okay. And then we put these in here. Ta-da! Like so. And what's this one? 5. I think this was 5. Yep. So, and in all these, oops, I have another one here, 3. All of these don't go in here. We have another box for those. And we won't put the ribbon in there either. No go. Just the connectors. Like so. Let's just put these over here out of the way for the moment. Watch out for my multimeter. And then we have this instrument. So this is your basic crimpy thing. So, not bad. Okay. Have to try crimping some wires later. And we don't need that. Do we have a little locky thing on the side? Yes, we do. There is a thingy somewhere. Oh, a tension thing. Interesting. Yeah, there we go. That locks it. Okay. That can go over here. Now, let's take another item. I'm going to need that. This one. So this was, I think this is the screen I was thinking about. So we don't need that. So this particular one, right, goes on a Raspberry Pi. But we don't support you installing this on an existing thing. Get bent. I mean, if drivers for this thing is a module, I should be able to put it in Linux. Give me a break that I have to wipe out an OS on a card just to get you running. That I thought was very, very stupid. But in here is a... So this is supposed to be both a panel. Is it just a panel in here? See, this is the funny thing. This is a slightly different version of this one. See? Raspberry Pi version. But you can see this. Look. We take this one and look at the bottom. Right? 300 gens for Raspberry Pi SPI support 480 by 320. And this one is 480 by 320. And it is 16-bit, 18-bit SPI TL. So 2 different ways of doing this. Interesting thing about this one, see, they don't use all the pins. But it's the same idea. I figured I'd put one of these things on this Pi right here, so that I can actually see what's going on. Or a different Pi. I don't know yet. So this can go back in here. And this is the shell for it, I suppose. And this one here can go back in here. It's the single bar one. So we'll find out which one is the... no, that belongs to you. We'll find out which one is the better one. So one's that. And this one with its silly document thing. Oh, we don't support. Yeah, right. Okay. Well, come on. Get in there. There we go. We will find out, won't we? And of course, like anything you unpack out of a box, getting it back in the box is not easy. But I think I've managed it. Ooh. Except for that part. Yes, the instructions don't want to behave themselves. Okay, so that's that. That's that. Now we have an envelope here. All this is DuPont ends. I figure I was going to make a few mistakes. So I bought some extras. They're like $1 a roll or 80 cents a roll or something like that. So there we go. All these, and I don't need that. And the last envelope I think I have over here is this guy. Yes, but these are all right angle ones. I think they should be all right angle. Yeah. I was doing things like this, and you see these holes off the end here? Like that. Yeah, I can make vertical ones, but I wanted some right angle off those type of ports. right? And then I noticed that some things I had here too, like this display thing, I had made them all verticals. It would be nice if they were actually right angle ones. So, and then I realized I had hardly any right angle ones. So, doink. And that, as they say, is the mail. Now, where to put things? First of all, just to get, just to get some stuff out of the way, like these. We will deal with you guys later. Call this the collection bin of things to be sorted. And we will put this over here. And I don't want to lose this card. Doink. And these two guys can go down here. Doink. And that can stay there. And put this back under the lamp again, because the cord gets in the way. So, that is all the mail I have for the moment. Tomorrow, I get those bins, and I get Sunday. I get the paper and the MVME, and hopefully next week, because it says it's in Calgary somewhere. Yes, if you buying things, it seems that you're getting lots and lots of tracking, which is really, really good. Now, I have a bit of good luck this week. I had a epiphany. Oh no, not really an epiphany, but this guy. So I found some interesting things out. So this is, yes, I need to clean my printer. It's not very dark and stuff like that. This is the page out of the Texas Instruments 74HC595 shift register. And if we go and find on my little browser here under the Adafruit, let me see if I can find it. No. I have so many freaking tabs open at the moment. It's unbelievable. Let's see. Overview, Funhouse, installing. No. That's the library usage here. Yeah. Okay, this is the one. So let me bring Chromie back up online again. That's not the right Chromie. Yoo-hoo, Chromie. Let's pick the right Chromie usage. Doink. That Chromie. I need to make some scene transition stuff in OBS. I haven't really done that yet. Anyway, so this is Adafruit's version. What is that? What am I on? That blue. Is that desktop? Yeah. Hide that. There we go. This guy here is Adafruit running a little Feather M4. And this is little itsy bitsy M4. So my little itsy bitsy is smaller than their Feather, but it's the same. It's the same idea. Now, interesting thing on Adafruit's version, if you look at all these blue wires right here, they go from pin to resistor to, I think it's let's see where they're plugging the pins in. If this Feather is okay, so resistor from LED plus. Yeah, so the positive side of the LED. So I built mine according to Adafruit's. When I first built it, it was different. It was pin 2, and this is where I always forget. So I get out my little ruler here, drink, and the plus side being the anoid. So positive of the LED to the negative LED to the resistor to ground, and they would have me go to ground and also along ground have a 0.1 microfarad capacitor going to VCC. That's a decoupling capacitor. It's supposed to smooth out the signal in the data lines so that we don't get noise. Fine. When I set this up, it didn't work. Didn't behave itself. But when I switched over and did it Adafruit's way, which is different, they're having the resistors go from the legs here. So this first component is actually the resistor. Then it was plus. Then it was ground. So these were flipped around. It works. The LEDs light up. So that, I'm a little puzzled electrically why it's doing that. I need to go look up this. Figure out why it's doing that. Why the resistor. And I heard too that depending on the LED you use, when the voltage requirement, the current it pulls, you can get away without actually the resistors on some colors. So I think if you put blue here, for example, and you run this at 3.3 instead of 5 volt, it'll actually, you don't need the resistors. But anyway, I built it this way, hooked up the Itsy Bitsy, you know, kind of 10 times checked. I made sure I had the, this guy here, which is ground to feed some power. This guy is positive, no, ground here. This is power. And believe it or not, I am running this whole system on 3 volts, 3.3 volts. This guy simply is here to bridge the power from this side to this side. Now, one thing to observe on some breadboards, and it's not obvious on the first go, sometimes this part of the bus and this part of the power bus are not joined here at the center. I was puzzled when I was fiddling because I have some other breadboards where it is joined. There's one continuous, right? And I think this is, if you got those white power bar breadboards, the pure white ones, they're like that. If you got these colored ones with the colored lines and the numbers like this, they have this split personality here sometimes. So I did all that. Okay, solved power problem. And then we have cable select line here. Mozzie. Now, Adafruit's in a big binge to change all references of master slave. So if you look at the GitHub, it's all, what do they call it? Main now. It's not master. If you look at all their definitions of MISO and MISO and Mozzie, so they'll now say microcontroller out, serial in, or microcontroller in, serial out. Although if you look in a lot of documentation, of course, it'll still be master in, serial out, master out, serial in. So they consider in that term, this is the base and this is the peripheral, right? So base out, peripheral in. So that's what Mozzie is. Now I saw one other guy on a YouTube call it Kozo Kizi. Controller out, serial in, controller in, serial out. That will not catch on because everyone will just go back and call it Mozzie and Mizzy. Because that's what's written on these things. That is what the docs say. It's just the actual expanded anachrony wording that will affect it. So I set it all up and I put in this default code down here. So let's go down to, so there's that example of them strobing the lights two times and then turning lights on 3 times. So this code right here. Now, let's see if I can make this a little, is the Chrome locked? Yes, it is. Let's make the Chrome a little bigger, see if we can, there. And let's slide that little square there to the edge. And in here, we'll go, So basically this code, okay? So there, I found that there's basically 4 different library sets that you can use to control a shift register. So this is number 1, and it is the shift register, this guy, basically the Adafruit 74HC595. Okay. Now, in this code, you do not see this, but there is a 4th parameter here on the end, right here. So latch pin, whatever. So I'm just going to open this up. We don't even have to go into the thing. We're just going to go in here so we can look at the file. So this is another issue I was having with the mounts disappearing and not appearing. So let us move this over here. And I'm going to change from Chrome. I'm going to add desktop here. And let's see if we can add the desktop. Yeah, there we go. And we'll turn Chrome off for a sec. So, and of course, Chrome is interfering. So I'm just going to lock that and unlock the desktop so we can make it bigger. Let's stretch down, 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 like so. And you won't see my face unless I put my face higher up than the desktop. So here's the Pi directory, and let's go look at the file. I'm just going to go open up thing, and we'll open up the Itsy Bitsy workspace. Okay, and if we go to CodeWorks for example, so here we have, yes, bundle updated. Here's the same code. And if we rename code here, and we're going to call this code 4, and CodeWorks, we're going to call code. You can only have one working root Pi file here, so you have to do this. Okay, so here it is. And we'll go in here and we'll just save it. There it is. Okay, so now I'm going to just make this a little smaller so we can see the bottom edge here a little bit. So, strobe, on, strobe, on. There we go. All working correctly. Okay. So, I found of the 3 boards I've been messing with, so we have 4 boards. We have Metro Express here, M4. We have the Grand Central. It's in a bin over there. We have the Pico. And we have, of course, Itsy Bitsy. And we also had a standard Arduino. So this is a Keystone Arduino. It's no real different than any other Arduino, except they've added extra breakout pins on here. So, but it's basically the same thing. So I can get all that working, but I found that I was getting noise in the Metros, but not the Itsy Bitsy. Noise is meaning literally you touch this data line here and you can cause the LEDs to go on and off and stuff like that when the code's not even running, right? But it's working. Now, one thing I did in some code, let's see if I can find a sample of that code. Yeah, okay. So right here, this is the 4th parameter, by the way. So this is very similar code to the other one I was messing around with before. So shift registers number equal 4. And then you pass the number of shift registers to the SR object build. And the thing is, this, according to their notes, this is supposed to be able to chain shift registers together. And I was messing with, of course, this guy right here. Now, if you remember, this guy here is 4 shift registers. The object of the game on this was to send 4 sets of 8 bits, 3 for color, 1 for row select, basically. Where on the row the RGB is turned on. And now that's a little tricky too. I found, for example, playing with this, and I got the code kind of working on this one. Kind of did, but not with this code. I could not get for the life of me this to deal with that panel properly. Just didn't want to work because it seems like this code is really built. I'm going to go back to code here. This code is really built to toggle, literally, like you look at this one that it says pin 1 and you're cycling through this, but to that, this is a whole row. I need to go finer than the pin. I would also have to say in here, pin, 0, comma 1, for the first pixel, turn it on, not the whole row. And this is what was happening. If you hook this up to this guy, the matrix, it just turns a whole row on. And then it actually cycles all the rows, and then it blinks 3 of the rows on, off, on, off. So that's why I went back to LEDs just to get a hang of all this. So it was running So that was method number 1. Okay. So I'm just going to rename this back to code dash works. And our code for here, current one I was working on here, rename code pi. Yeah, I have too many code windows up. Let's just close some here. Okay, so this guy here. So as I put the note up here at the top, this is the second method you can do. You throw out the shift register stuff, and instead you go for, let me find it on the web here. This will take me a moment because, of course, my bookmarks aren't really sorted for this. Pinouts, Adafruit, introduction to Adafruit bitbang libraries. Pinouts, search tab, SPI. Okay. Yeah, okay, here we go. So bring Chrome back up for a sec. Okay. So what we have here, wrong Chrome apparently. Properties, let's bring up another Chrome. No, not you. Not that Chrome. Properties. Let's bring out not the shift register one. We need the SPI devices one. Okay. So here is where they talk about SPI protocol. Uses 3 to 4 wires, and this whole doc is about two types of protocols, I2C and SPI. So there's, for example, my Metro Express. Okay. But this is the older one. Mine is the Metro Express M4 with the purple board. So here we are. They're first going to go and do I2C. They said a bunch of stuff. Oh, are they doing SPI in this one? Yeah, okay, so this is the SPI section. So what I was throwing me for a loop in here was not this top part here where you initialize everything. And what I also did in here is, because I kept changing pins around on the code, and let me just turn off Chrome just in the code here, I define board clock, MOSI, and CE like this right here, so that I can fiddle with this all the time. I could change these values, and I didn't have to go running in the code trying to find every occurrence of it, right? Hey, and get back to Chrome for a sec. So here we do all this fine. Now, as I said before, the only problem with these demos, they're all reading from an SPI device or reading from an I2C device. Fine and dandy. I was more interested always writing to the device, not necessarily reading to it. So we come along down here to this piece of code. And by the way, one of the guys at work said to me that this while loop is really stupid. They don't explain this well, and unless you're a Python programmer, this pass right here is the equivalent in assembly as NOP, no operation. It's a dud. It just does nothing. Next, we have here a loop that says basically while not try lock. Well, one of the things I found is, okay, what state is the lock in? Is it enabled or is it disabled? And I was having no end of headache with this, right? So they come along here. They configure this SPI, right? They bring this false, right? They fill the result with a read. They read into the result, blah, 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 this sort of stuff. And they flag this back as true. And they print out the result. And here's this byte array of 4 bytes. Okay. Well, apparently, this is one of my biggest issues with this. There was not a clear explanation of what was really going on with this. I had to go back, look at the data sheet, and look at other people's samples of blinking the LEDs with a shift register. Now, I'm talking about ones where not even this board that's in here is in play. All there are is they put buttons on the breadboard, and they said this button, if you click it, does this pin. This button, if you click it, does that pin. So if you hit this, it does the clear. If you do this, this toggles the cable select or the latch pin or cable and chip enable, right? Whichever one you wish to call the thing, right? So from in piecing all that together, I realized what was going on here. I had a brainstorm. And after talking to my friend at work about some of the code, at first he thought it was the reason I was getting the lock being all false all the time or all true was a threading issue underneath. But then I realized about this piece here. So you really have to look at this again. So take all this while loop out crap out. And this is what I personally did. Instead, I changed it to, and I'm going to have to flip over to code here again. I changed this. Can I zoom this code? Just a sec. I seem to be on something. There we go. Can I zoom? No. Control Alt. Control Shift. Alt Shift. Well, there is a way. If I knew how, I would tell you how I would do it. But let's see. Let's take the lock, not off Chrome. Yeah, off the desktop. Let's. No, the desktop has a. Doesn't have a lock. Yes. There we go. So let's move this a little bigger, so we can see. Okay. Put the lock back on again. Okay, so what I did in mine, so not only did I break out this so I could separate the pins out, and then I did this. I wrote some notes here. Okay, so this is setting the pin. Now, according to the data sheet, when the pin is high, right, you can't send it anything. It's not going to output anything, but it's ready to accept data. When it's low, that's when you trip the shift register to dump its contents out, the pins, the parallel pins. So what we had to do, I set an LED clear array, all zeros, an LED set array. In this case, since I'm only doing 8 LEDs here, right, on the thing. I wonder if I can move. No, I can't. So the problem, of course, on this, I'm missing one of my cams at the moment, and it's because the stupid USB problem I'm having on the desktop. So I have to shrink a little bit. So these LEDs, basically in the code, I had to go and, have a clear, have a set, and this is the pattern I wanted, for example. So what I did instead with the while loop here, I first of all set a variable up for the lock. Now this is one thing I'm still unsure of. Just setting the state here based on the lock. Did I execute the lock, or did I just read the lock's object and find out if the lock was on true, false? Okay, so this is where you'll find a ton of debug print statements. Check again the lock state, print out the lock, find out what's going on. Right? Loop is random. Instead, I turned this into a 4 because I wanted to test this out. So then what I did in the loop is I said, if the state is false, right, then unlock and try locking again. Right? Else, if this lock is true here, clear the LED. So make sure the CS value is true. Try a lock. Write some shit to it, set the value to false, which trips the chip to operate. So I should be sending 8 zeros out to the chip. I come along and I do it again. This time I check the lock state again. This is my debugging. I can remove all this stuff actually now. And I look and I say, well, okay, I have to configure the SPI. Again, I bring the CS chip back up to make sure it's true. I do a configure, I do a false, I cause the action to happen. I come along, I do it again. And this time I say check again. See, try to clear the LEDs, right? So again, bring the CS line to true, write zeros, bring the CS line to false. Bang, all the zeros go out the thing. Okay, so set it with the LED set variable. So if you saw 1 0 1 0 1 0 1 0, okay? So chip comes high, we write the values out, a little bit of a sleep to have it settle down. Yeah, I don't need a 1 second sleep, by the way, and then bring the CS line down to false. Bam, those 8 bits are written out to the LEDs. Okay, we write a clear, right? And then finally here, we bring it back to true. We unlock the bus. We bring it back to false. And then we check the state again. Now, if we go and just move this up here like so, and we connect to the serial monitor, right? And we go, we should stop this, okay? So we'll go back to the top. So you can see it's stage 5, stage 6. Okay, we'll start at stage 1 there. Check again, SPI lock true, configure SPI, right? Okay, good. State is true. The lock state is true. Try to clear the LEDs. Clear LED with blah, blah, blah. Good. Set LED with the byte array XAA. So it's not 3 letters there. The X represents hex. Okay. Set the lock state back to check it. It's true. 4, it's still true. We run a clear. Step 5, check again. It's still true. We unlock. Step 6, right? We check state lock. I think it's state 6. Yeah, print. Check again. SPI 6. And see, this is where I was running into an issue. So the state says still true. Oh, we don't have a thing after here. But see, in theory, I unlocked the bus right here in the code. But at step 6, it still thinks it's locked. It's still true. So this is the funkiness I was getting with this whole SPI system. Okay. Is that I was stuck in one state or another. But as you can see, we just go Control D again to start this all over again. We are looping through and blinking. And to prove that, if we go back up here to our byte value, where we set 101, this time we'll go 1, 1, 0. So in theory, like so, first 4 LEDs should go on. The last 4 LEDs should go off. We save it. There we go. 4 LEDs. First 4 on, blinking on and off. Last 4 not on. So there's our byte pattern. And it works. Now this was the SPI method. Now I was also working on, let's see if my code is in here. No, not these ones. Try these ones. Yes, as you can see, I was really messing around. 3, 4, number 6. Okay, so this was the BitBang SPI I was trying out, and I think 7. Yeah, this is the SPI device. This is where I was up to at the moment. It was to play with the SPI device. Now, according to the docs about this, the SPI device library handles the CS line for you. As you can see up here, it says A1. Technically, on the Itsy Bitsy at the moment, I am running off of D10. So, this is actually wrong. And this is what makes this easy. I just go like that and change the pin and then save it. So this won't run because, of course, it's not code.py. It's code-7.py. So, but this is I was messing around here. So they have this overall object that you can do things for here. Chip select equals 1, chip right blah, blah. So based on the regular SPI, what probably has to go into here, right, is device chip select equals 0, like so, right? So we come around, we have this byte array, we enable, make true the CS line, we write the byte array out, then we do 0, we dumped the chip, and then we see what happens. Okay, I'm not going to bother going through this because I still have to do more troubleshooting. Well, that was that mode, and we don't need 3, we don't need 2, we don't need 2, we don't need 1. So in 6, same idea, but this time this is the BitBang version. So we're not going through the chip specialized SPI system. We are going out 3 data pins. As you can see here, D9, D7, D10. We're setting 1, 2, 3, clock, MOSI, CA. There could be, in theory, here the 4th pin, MISI, right? But we're not doing that. I cannot read from the shift register. This is not that type, but I can write to the shift register, right? No, I would, if I wanted to read, 9 parallel bits coming into the chip, reading it from serial and dumping it. That's the other type of shift register. That is the piezo, parallel in, serial out chip register. And I do have them. Hey, in that box of chips I got, it's in there. The idea behind that chip is you take a 6502 or something like that, and for example, you want to read the data lines on the chip. You hook that up, and you can then serially get, the 8 registers or whatever it is. I haven't got that far yet. Thing. I mean, if I wasn't getting past this, there's no point in going to that yet. But that's what this is. And now I've also been messing around with this line basically. Remember, I need to send bits to this thing, i.e., 1 byte for 1 shift register. If I'm going to deal with the RGB matrix, I need to send 4 bytes. And this is what I was messing around. So this code looks a little weird because it was not rigged for the LED. I'm going to actually change it on the Itsy Bitsy so that this is oriented to do this. I want to see if I can get all 4 methods working. So I want to get 74HC595 library, SPI library, SPI device library, and finally BitBang, all doing exactly the same thing to this thing. Period. Right? Okay. So, let us just close this, and our workspace is saved. I was messing around a little bit with Git on this thing. I'm going to have to change my approach to this. On the Grand Central, on its drive, I actually knitted the Git there for the code that's there. And technically, I have a whole tree of the code from the Grand Central on my Git repository, so that I can have a backup of it. Because I literally was blowing up the Grand Central board on a regular basis, literally screwing up because was it this system doing it or the previous system? So the other board, and I think it's might have been the power supply. I'm not 100% sure, but I was just turning off for no reason. It wasn't doing that before. So I wasn't sure if it was the OS causing the issue or whatever, or the power supply was kicking out, or this board was kicking out. So I switched over to the i7 system over here, and now, of course, I have USB issues. And one of the issues is the USB bus going nutso all the time. And when it does, you lose the CircuitPy drive. You lose the drive, guess what? Your file system was dismounted incorrectly. Oh, I cannot emphasize on when playing with these boards, bloody well close the file system. So just don't unplug this thing. Go right away, close your workspace, like so. Go to USB removals, safely remove. So it's dismounted correctly. Otherwise, you're going to get a file system with a dirty bit, and you get corruption, and then all of a sudden you start getting these effects where this will report Oh, I'm sorry, you've written the file system, blah blah blah, and it goes on and on and on. It's like you just blew everything up. So sometimes you can go fsck.fat, check that. Oh yes, the dirty bit's still enabled. Remove the dirty bit. Do a check. Fine, things might be good. So then you remount it, and whew, everything's there. So make sure you have backups of the what's on the board's drives. So like this guy. So we're gonna turn this on, and I'm saying I have to shrink the this to give us a little more window space here. So here is the Metro Express M4 and the RGB matrix. So this is the state I am at with this one. So we're going to plug it in. Okay. And yes, the LEDs are blinking. So we come back. See, this is the problem. This is you. I just plugged it in. It should have registered. So the only way I found to cause a trip on this, since we haven't mounted the file system, you can try double click this. There's the Metro boot. Click one more time. There's the CircuitPy drive. This is not the fault of this. It's the fault of the USB bus. It's like stuff is not coming across it correctly. And it's the reason why the third cam, the fun cam, that has the angle on the desktop, is not working either, is because every time I try to access it, the bus chokes. And it doesn't matter. I could be on the USB 2.0 bus, the 3.0 bus, whatever. It doesn't like it. Period. So here we go. CircuitPy, F5. There's all the files on here. So we come back here and we go Metro 4 Express Workspace. We'll open it up. So as you can see, I have all the libraries in there for various stuff. And here's the code I've been working on at the moment. Okay, it's very similar to the LED code from the Itsy Bitsy port. In fact, oops, that's wrong. This is not Itsy Bitsy. I borrowed the code thing. So this is Metro. I can't spell Metro Express M4. Okay. So we're doing basically the same idea, same setups, but here we're getting a little more complicated because I was playing with bits because I'm playing with the LED here. Okay. So I was testing out sending actual bit patterns or sending hex values. And I was also playing with setting the red, green, blue, and row based off various things. As you can see here too, on row select, if you send it a 1, the first row. If you send it a 2, second row. You send it a 4, third row. 8 is fourth. 16 is 5. 32 is, right? And then on the RGB, this I started messing around with. Like, I mean, that was my kind of my init. This is actually incorrect. It's supposed to be at the moment. But in theory, yeah, actually that was correct. I was defining the thing. I'm so still used to doing C stuff where you have to define an array where in this system, Python, you don't do that. So here we are trying to set the zeros. Then we go and set LED set 2. We set the values into this array. So whatever the value of red was, whatever the value of blue was, what the value of green was, what the value of the row was, right? And it just so happens on this one, if you're wondering why the values are 66FFFF03, it's because, did I put the code here? No. The Arduino sample for this panel, right? Control S. The Arduino sample for this panel, the first line they pushed through it was this value. So they had this big long array of values here, 66. And when it turn, as you can see on this, I have to restart this because I made the loop very small. So let's make the loop a lot bigger. Let's make it 50. Control S. So, see, we're only blank these sets. Well, the idea behind it, I'm not supposed to be blinking the bottom row. I was supposed to be on the next row. That's the 66. The first value in that array was actually a 0. So, or 1 or something like that. And this is what I'm working out. I'm trying to translate the C code over here into Python equivalents. So I wanted to get that heart test going that they had. So if I go back to the browser for a sec, do I have that up? ITC, no, not in that browser window. Let's try this one. 8. There was a, let me go quick. Retro using Pino, Arduino, Robotan Mega, LCD, GitHub. No, it's not the one. 8x8. And SPM. There was a, you know, I thought I put the wiki page aside. Maybe I did it on the other machine. I have a wiki page with this code. Let me just see if I can find it. Getting started. Not that one. Driving. Upload. ESP32 cam. VASM. Did I put it under? Let's see. No, it's all those. Oh, this is great. I keep losing this link. How did I find it last time? Here, I'll show you what I'm kind of doing here. Properties, and we need to change this. No, not that one, you moron. The Chrome one. Thank you. And we are doing new tab. Nope, not that guy. New tab. There we go. So what was I searching? So if I search on here, LED Matrix version 1.0, that's what I was looking for. Not those. There was a tutorial for this. I don't think is it this guy? Nope, not this guy. Not Grove. Seed Studio. Is it this guy? Nope, not this guy. Right idea, wrong one though. This guy. Okay, so if we scroll down, in fact, this articles were updated recently because in here is Pico. Pico's really new. So, but we were interested in, I was looking at this code. So what we were interested in was this static array right here. So they're sending, so they have their 4 bytes right here. They do their, this is on a Pi, by the way. They define their red, blue, and green data lines, 0, 1, and 2. So 0, 1, and 2, right there, this block right there. And 3 being the row incrementer. So they're saying here that they have this heart with 8 pieces in it. It's a heart. I mean, I have the Arduino program to show this, but so I'm trying to do the next piece of the heart, right? So I'm effectively saying I've already gone through this loop once. I've shifted this, J being 1, right? I think it's 1, right? And the heart being 1 from 0, right? So we're at member number 1. So this should be 1. This should be 1, right? And this is what I'm trying to write out over here. But as you can see, I'm not doing it correctly. So that's what I'm doing. But at least on this, I can like change things. So if I change this guy up here to 0, for example, I think 0. I think that'll work. Am I reading? Which one am I writing out actually? I am writing out loopy, lock, unlock, value, lock, clear. Here we go. I'm writing out set 3. Okay, so I've been experimenting with set 3. That's set 2. Where's set 3? Here. So if we go like this, 0, 0. There we go. We just changed this all to solid on. If we were to go, I think, FF, nothing's on. If we go FE, for example, see? So we are now kind of controlling this. I still don't have a rock solid understanding of why I'm turning on, for example, these 2. I don't understand exactly the row selector exactly. There we go. I managed to get 1 pixel on. This guy right here. But to me, it doesn't kind of make sense why, if this is like the Android code over here, so what we're doing is writing element 0, then this element, then this element, then this element. So in its essence, we're going 0, 2, 1, 3, like that. Okay, so this 0 to them in this Android code here is red. So this is red, this is green, this is, red, green, blue in the code, in that order. Let me just flip over to back, getting out the Chrome out of the way. So in my code here, and I'll make this bigger. Yeah, we have to unlock it, of course. This guy here. So in this array right here, so red, yeah, get out my tools there, red, effectively green, blue, row, like this, red, green, blue, row, if we're matching the Arduino code, basically. So this is the state I'm currently in. This is good. Before it was completely pure garbage and random. And the other thing is, this is just going off and on all the time. Now, not responding to crap anymore. So, but basically it's a variant of the LED code that I was running on the breadboard, but designed now to do 4 bytes instead of 1 byte. Oh yes, I only was running for 50 loops. So that's where I am on this state. And again, as I said, when you're not working on this, better do a file save all. I changed stuff. There we go. Course is close to workspace, like so. And safely remove, like so. And unplug. And voila. So overall, this has been a good week. I've discovered a lot. Now, some of you might go, oh, this is so easy. Well, I've never done it before. So I'm the type of person who will sit and grind at it and problem solve it. And we don't need any of that up anymore. So let's go turn the desktop off. Except, got to move the mouse all the way up 2 monitors. Right? And I'll just do locks on these. So that's the state. I'm hoping I'll get the CPU next week. And then, of course, next weekend, I'll rebuild this whole box. And we'll see where we stand. I do have DDR4 RAM for it. I do have a cooler for it. Since it's only a 65 watt part, I have a 105 watt cooler. So it's more than air cooled. It's more than enough to keep quiet and run that Ryzen at anything I want. I'm looking forward to actually working on that board because the one on my main machine, beautiful board. Everything works perfectly on it. Except I found out I might not have TPM turned on. And if you've been watching the Windows 11 spew on the net, there's some really nasty things they're going to do. I don't know if you've heard. Some of the things apparently is that stupid, your taskbar down here at the bottom here. Let me turn the desktop back on for a sec. Right. This piece, I don't need this. This piece down here in Linux, for example, where your apps are sitting on, your launcher, your start button, all that sort of stuff, right? Classical Windows-oriented looking bar at the bottom. I happen to have mine in more Windows 7 style menus on Linux, but I could have it differently. Or in Windows 10, you would see this type of tree plus the tiles over here, which are all adjustable. Not anymore. Gone. This whole bar is centered like a damn Mac. You can't move it at the moment. Gone. You cannot. This bar down here, I could put this at the top of the screen, the right side of the screen, the left side of the screen. It doesn't matter. Not anymore. Windows 10, yes, you can move that bar anywhere you want. No, in Windows 11, you can't move the bar. You're stuck with it in the center. You cannot even group icons. You cannot even put an app in, like I have True Launch Bar on the Windows 10, that when you hover over an icon over here, it pops up a menu of things, i.e. it's grouping groups of icons together. Nope, can't do that anymore. It's all gone in Windows 11. It's really soured me for wanting ever to upgrade to Windows 11. It's the same stupid crap that happened when they went from 7 to 8. They didn't learn their lesson, right? People like the interfaces the way they were. There will be a group of people who go, oh, this is the most beautiful thing, blah, blah, blah. But then they'll go realize, just like in Windows 8, where's my damn start button properly on this side? Where's my grouping of icons? Why can't I do this? Why can't? And they're going to it's going to just hit the fan, right? So I think before they actually release the thing, they better well address some of those limitations in Windows 11, right? Yes, the interface looks really nice and all that, but sorry, I don't want a center-based toolbar. I don't give a crap if you're touch-oriented, right? These monitors aren't touch. Those monitors over there aren't touch. I don't have touch. So why in the hell are you forcing me, just like Windows 8, back into a touch system? Get bent, right? It's like stupid. So go watch the Windows 11, especially like the Linus's goes through it in a bit, and you'll see what I mean about the crap that's going on. And he just updated his Windows 11, and he went over some of these finer points that was in the fine print, but not talked about in the video. And there's another thing. You're going to do this big splash on the world, right? Effectively, you're doing, streaming the video. Hey, if YouTube can do it, live to thousands and thousands of people, Microsoft, bloody well you can do it without it crashing. I don't know if you watched the 11 thing. It was constant hicks in the videos, streaming problems, you name it. Holy crap, that was bad. They could have done a lot. That was really showing off. And you expect us to think that you're ready for all this? No. But then again, it's like they're not listening to people. There was another piece of nasty. At this state in the build, you have to be connected to the internet, and you have to have a Windows account. No local accounts. Meaning, if you're a Windows 11 user in the rural area and you don't have spotty or no internet most of the time, you can't run Windows 11 because it won't let you. You have to connect to the internet, and you have to log into Microsoft. Right? Dumb. Utterly dumb. There's going to be scenarios all over the place, and this is talked about so much in the news from the U.S. How much percentage of rural America doesn't have adequate internet at all? I mean, it's kind of why Biden's putting $35 billion, or he wanted to put $100 billion into it, but of course the Republicans are being asswipes on it, and to grow out infrastructure, right? Wow. But you should go check that out and see for yourself. In the meantime, it is 1:23 in the morning, and I think I'll cut it here and push this up so that tomorrow morning I can verify it's all good. It takes a while for YouTube to suck these things up. So for the wee hours of the morning, this is it. I will get back and I'll show more once I figure out more of the RGB matrix. And when I get some more parts in, waiting on some stuff, and see, maybe I will, show it off again. But of course I'll show it off. Duh. William, don't be silly. This is the end. Kind of like the song. This is the end.